made up of. So let's look at its order. It's like, okay, well, a prime divides the order, so let's multiply the group by powers of that prime and find out what subgroups disappear.
Yeah.
It's like, okay, by looking at what disappears, it gives us a way of figuring out how it's broken down.
Mm-hmm. The decomposition, yeah.
Seems like you could even make a kind of game out of it somehow, where they're told, okay, here's a group of order 72, and you're allowed to ask certain questions to figure out exactly what its decomposition is. So you say, okay, well, what happens if I multiply by 8? It's like, oh, well, if you multiply by 8, this particular subgroup disappears. It's like, oh, okay, now I know more about the group. Let's see how many questions it takes me to figure out exactly what its decomposition is.
Yeah, except Rotman decides that examples such like you gave are not at all necessary. He
no examples
of vector spaces.
All right, so I'm game to just start walking through it.
Okay.
Maybe as we I'll understand better than I do now.
Yeah. So the direct sums part, I believe. The thing is, you can't pick and choose which one is necessary because you don't know if he's going to come back to it, or because he does come back to a lot of things. So the direct sum, we'll go through some of those, but like there are some like important things, and others are kind of like generalizations of those. Like this one, for example. Here, this is just like a generalization for what you had in the case of like when you had two summons, and the proof is pretty much the same. Other than that, we have got the pre-Abelian group, of course, that's a big thing. And for Basis Theorem, we have got these. And yeah, let's see. The Fundamental Theorem, I don't have much idea about it, but I guess you've done more than me, so we'll see. Did you look for Hungerford? Is there anything good there?
Yes. There are a couple of different ways of describing the fundamental theorem. One is in terms of primes, and the other is where you have it's broken down into subgroups where the order of each subgroup divides the next one. Do you know what I'm talking about?
Okay.
See the ones where it says D1 divides D2 divides D3?
Yeah.
And different books seem to they just have to make a decision which one they're going to go for first, and then which one they're going to derive afterwards. And Rotman goes for the prime or primary decomposition is like the main goal, and Hungerford does it the other way around. So it'd be wonderful to dive right into chapter 2 of Hungerford.
Chapter 2, yeah, this one, right? Structured groups.
Right where you are.
Yeah.
It's fairly easy to skim through the free Abeilan group part, and then the meat, so to speak, is in section 2 of the chapter. But a caveat he gives is that the proof in section 2 relies on a fact from chapter 1. It's like theorem 1.6 or something like that.
All groups are written additively. No, wait. Sorry, theorem 2.6.
There it is.
Uniqueness theorem, yeah.
Theorem 1.6 from chapter 1. And it's not something easy to breeze through. It's
Okay.
something that looks like this, with the M1 divides M2 divides blah, blah, blah. So I think what I'm learning is that there's not just an easy way and they're being mean to us. I think that there's just some tough stuff to get through.
Yeah, this is genuinely tough. Really tough. Yeah.
But the thing I like about what's happening over in Hungerford is that he's going to push us through this way of doing it, and then he's going to come back to those ideas again in modules. So at least you get to see the arguments twice. So maybe they'll make more sense the second time through. So when he gets to modules, which we are going to be doing out of Hungerford, he says you can prove this using the same techniques we did in chapter 2. You just need to substitute these facts for these. So basically, he just proves the little lemmas that you have to substitute in, and then follow through the same argument.
Okay.
So I didn't do it overnight. I was hoping to have a little bit more time. But I really want to go through Hungerford's proof of the Fundamental Theorem, so that when we do get to modules in a couple weeks, it's going to make better sense to me.
Yep. Makes sense. Yeah, that's a great idea. I think I'll do the same. Yeah. Okay, that's good. So Hungerford is something to go through.
And Hungerford has examples.
Yeah, he just doesn't have proofs.
Yeah, I used to not be a fan of Hungerford, but I guess things are relative, right? Like, well, I'm liking Hungerford better than Rotman at the moment.
Okay.
But I think that there's something to be said for getting through Rotman's argument. We could just end up deciding that it's super elegant and definitely worth the effort. So I'm going to give it a chance.
Yeah. So yeah, I mean, he does set up a lot of things. I mean, Hungerford doesn't ever mention like pure subgroups, does he?
No.
Right.
I just get the feeling that that's something that someone came up with, and either Rotman did it himself, or he just recognized that was a really elegant way of doing this part of the proof, so he adopted it.
Yeah, and he says that it is important. Yeah.
I made it far enough to see where that fit in to proof. So, I mean, he doesn't just introduce it for fun. It's definitely to make one step or a couple steps in the proof work out really nicely. Just he never really gives the big overview. Like, this is going to be broken down into 3 parts. We're going to introduce this for this reason. It's very linear, but there's just not the motivation put in there. I think I've complained about some folks being maybe a little too chatty. He's not chatty enough.
Yep. He's going to do it exactly the way he wants, and he wants you to follow him exactly like that. I checked the Wikipedia page. Yeah, there's this book called Infinite Abelian Groups. Infinite Abelian Groups, or yeah, something like that. Kaplansky, which I believe Hungerford also cites a couple of times. Yeah, I saw it somewhere, Kaplansky. It's a kind of short book, not really even a book, I guess, like a monograph.
Are you familiar with Fraley?
Yep. Wait, Fraley? I'm mistaking him for someone else, maybe.
Yeah, there's a book called The First Course in Abstract Algebra.
Oh, Fraley?
I've been studying from
yeah.
I don't know. there seemed to be kind of a snobbery against that book, like it was too elementary. But when I'm running into stuff that's as hard as this, I do kind of turn to it to say, well, did he find an elementary way to work through it? And he actually does have, he's got a section on free abelian groups and the theorem. And something that I think it was he who mentions Betty numbers and...
Betty numbers, wow, that's not elementary.
But not going into it, just saying that this is of interest.
Okay.
I'm looking at it, I'm not seeing it.
I've heard it. I mean, like, some people say that is a very good book for, like, undergrads.
Oh yeah, there it is.
Yeah?
Yeah, like undergrad. Yeah. But again, a bit of chattiness, like, oh, you might be interested in this, but it mentions the Betty number of the torsion coefficients.
Yeah, but doesn't talk about them.
Here it says, we give some exercises that indicate their uniqueness. Oh.
Okay.
So I think that's the fault of Fraley, is he shows that there's a decomposition, but I don't think that he proves uniqueness unless that set of exercises actually constitutes a proof. So, I mean, whichever thing we use, including Rotman, he's actually carrying out two things, showing out that the decomposition exists, and also showing a kind of uniqueness.
Yeah.
So that two groups have the same decomposition, and it gives rise to some set of numbers that we can use as an identifier. The two groups have that same set of numbers.
Yeah, that's...
And they're isomorphic.
Right, so that would be... That's like it, the whole time I was thinking of field and vector spaces analogous to that. And I believe he also makes the same analogy a couple of times.
Greetings, Hearn. We haven't really started yet. I think we're just giving our impressions of the reading for today.
Yeah, I haven't got up on the reading yet, but hopefully will in the next week or next 2 weeks.
Yeah, the coast is quite fast, but yeah, hopefully modules will be easy, as I also hope. Hey Brian. Okay, so we've got a lot to go through today, so let's not waste much time. But okay, so we've got to talk about finite abelian groups. So we'll be talking a lot about direct sums first, a lot of properties, then we're going to prove one of the important theorems, the Basis Theorem, and then we'll go to the Fundamental Theorem. Hopefully all in today's time. And wait, yeah, I think yeah, this was the journal. He gives like very short proofs. I haven't gone through them like seriously, but doesn't look that bad. Yeah, Rotman says this is the shortest proof for Basis Theorem that he has come across until now. So, yeah. Okay, so this is Rotman's Advanced Modern Algebra, Chapter 5. Okay, so we'll start from direct sums. We'll be skipping a lot of proofs, because either they're easy to read through or easy to work through yourself. because I've got a lot of them. So direct sum, Rotman defines two kinds of direct sums, the external and the internal. So the external direct sum is essentially the Cartesian product with the addition on it. So you have this as the external direct sum, and its elements are the n tuples of these S1 till Sn. All of them are elements of the abelian groups that you're taking direct sum of, right? And the binary operation that you have on this external direct sum is that if you take two tuples and you add them, the tuple that you get is just the addition of each of the components, or each of the elements of the tuples, right? So that's the external. The internal is when this the external is like, it's the same thing as just like using different language. You're using the subgroups of a given group, and this group G, which you're taking subgroups of, is actually isomorphic to the the external direct sum. But as we'll see very soon, that they coincide to the same thing. Okay, so the definition of a direct sum is this. So you have G is equal to S O plus T. This is so you can write G as the direct sum of two subgroups S and T if S plus T is equal to G. That is, if you add in every element from S with every element of T, you're going to get an element of G, right? So every element in G can be written as sum of two elements, one from S and one from T. So that's one condition, and the other condition is that the only thing common between the summands S and T is the 0, right? So that's the direct sum. And of course, as you can guess, everything in here is abelian, right? They can be infinite or finite, that will be stated, but otherwise we have abelian groups. Okay, so the first proposition, whose proof we're not going to go through because it's pretty trivial to go through that. It is that if you can write a group, an abelian group, as sum of two subgroups, a direct sum of two subgroups, then of course the first thing is every G has a unique expression or representation as S plus T, right, where S is an element of the subgroup S and T is an element of the subgroup T. So that's one thing you can get. The other thing is that if you have such a direct sum, then there are homomorphisms that take you from the abelian group G to the subgroups S and T. They're called the projections, just like the typical projections we have met in categories and at other places. And you have injections, which are basically inclusions. They include the subgroup into the abelian group G. And as you can guess, the projections are surjective, injections are injective, and these conditions hold. And this is not that hard to see if you think about it. I was able to make sense of this by just drawing some diagrams, but yeah, when you have P composition I, you get the identity on S. Q composition J gives you the identity on T. Pj together give you 0. Qi together give you 0. And to get the identity on the abelian group, you have to have IP plus JQ, right? So okay, we're not going to go through the proof, so maybe it's better to kind of like draw a diagram and make sense of this, which is, I mean, it's not that hard to see, but maybe. So give me a second. So yeah, basically you have G, you have the projection P and the projection Q coming to S, T. You have the injections I, injection J, right? P and Q are surjective homomorphisms. I and J are injective, right? So what was the first thing? It was that PI is identity on S. So PI is first you do I. So first you go from S to G, that is I, then come back to S with P. So PI gives you the identity on S. Do the same for here. You do Q, J, you get the identity on T. Then what else? To get the identity on G, so if you want to have the identity on G, you need first you want wait. Okay, yeah. You want IP. So IP is you first do P, you go from G to S, then from S to G, you get something there, and then you do the same here, J, so Q, and you'll be you add these two things, and you'll get the identity on G. So this is all easy to check, but yeah, just for clarification. Okay, so that's that. With this, we're going to show how the external and the internal direct sums are basically the same. So this corollary says that you have S and T as subgroups of the abelian group G. If G can be written as the direct sum of S and T, then the direct sum of S and T is isomorphic to the to S cross T, right? And conversely, if you have two abelian groups S and T, you define subgroups S prime and T prime, which are isomorphic to S and T of S cross T using this manner. So this is just a way of saying how like taking direct sums in this manner is essentially the same as, you know, using the other format of, you know, tuples and the Cartesian looking product. You can prove this very easily. So you first do is you take a map from the direct sum of S and T to S cross T. So if you take an element in this direct sum, by definition of the direct sum, I know A can be written as sum of two elements from S and T, S plus T. So F maps A to an ordered pair S and T, right? And this is a well-defined function. This happens to be an isomorphism, which is not that difficult to see. You can directly see that this is bijective, right? For you have a one-to-one correspondence for every element in the direct sum to the ordered pairs that it has like a unique expression of, right? So this is bijective, and to check that this is a homomorphism is also trivial, because you take two elements, you multiply them, is equal to you know, taking the applying the function to the product of those two elements, right? So A, B, so if A is equal to S plus T, B is equal to P plus Q, F of A you know, gives you the ordered pair ST, F of B gives you the ordered pair PQ. You take the product F of A times F of B is equal to S T, the ordered pair, times PQ, that is just SP TQ, right? So that's the same as F of AB. So that's a homomorphism. So it's a bijective homomorphism. Thus, it's an isomorphism. Thus, this is confirmed. Now, the converse happens that you have two abelian groups S and T, and you take these subgroups. So if you take an ordered pair ST from this product S cross T, right, which you're trying to make equal to with the subgroups. So you take an element from there, that is G. Then G can be right. So G can be equal to right, S comma 0 plus 0 comma T, two order pairs that you're taking from S prime plus T prime, because again S prime plus T prime is just addition of all the tuples, and if you check the intersection of these two, you're going to get 0 0, because zeros are the only things that are in common. Thus each element of S cross T is also an element of S prime plus T prime. Thus they're equal. Right? So yeah, that was just basic stuff. Then we introduced something called the finite direct sum, right? So if you have this collection, this family of abelian subgroups of an abelian group, then you define the finite direct sum of these subgroups using induction, right? So induction, in the sense, you first define the finite direct sum for two elements, two subgroups, S1, S2, and then you increase inductively. So how that happens is, you first to get a finite direct sum of n plus 1 elements, you take the finite direct sum of n elements and then add the n plus 1th subgroup, and you take the direct sum of the whole thing. So this is the finite direct sum. So if you have three elements here, you first take the finite direct sum of two subgroups, and then take the direct sum of the third subgroup, right? So that's that. He gives an example of vector space. So of course, if everyone is familiar with linear algebra, you have a two-dimensional vector space over a field, and the field, they kind of view it as an additive abelian group. You take a basis which is xy. So if you have like the two subspaces that you get from generating from x and y and their addition, if you take the intersection of all these, they're all pretty much disjoint with just the 0 in common, right? So right, so this yeah, but on the other hand, if you try to get the whole vector space, two-dimensional vector space, from the direct sum of these subspaces, that doesn't happen, because if you first take the direct sum of this x and y, and then the direct sum with x plus y, that does not happen, because this direct sum is that is not entirely disjoint with the subspace you generated from x plus y, right? So yeah, that's a counterexample to this. Okay, so following ahead, we have a couple more important propositions. Okay, so this is just basically a generalization of what we've seen before from 2 elements to n elements, say 2 terms to n terms. So here you have G, and you have n subgroups, and you add them, right? So G can be written as the addition, the sum of n subgroups, and every element of G can be expressed as sum of elements from all these subgroups, right? So this means that this is direct sum. So this is the direct sum, and this is unique. This expression for every element of G is unique. Now, just like before, we had the unique condition, and the other condition was that you need where was that? Yeah, the intersection of the summands is 0. So here is also the same thing. If you have this sum of n terms, this is n minus 1 because this Si is excluded from the sum, right? So this sum excluding Si is disjoint with Si, right? So if you take Si intersection this whole thing, you're only going to get 0 as the common thing, right? And this, as I said, is just the generalization of the previous proposition, and the proof is pretty much the same. You're going to apply the induction again. Okay. The corollary that you have from this is, if you have G as the group generated by these n y's, now for all the integers mi, what you have is the linear combination of these integers with the y's is being 0 implies that each of these products is 0, right? So this, if you remember linear algebra, this looks a lot like linear dependence, stuff like that. But yeah, so if your G is generated by these elements y, and you have these integers and this holds, then G can be written as the direct sum of all the cyclic groups generated by each of the elements y's, each of the generators separately, right? And it kind of like directly follows from the previous proposition, but you just have to prove this kind of linear dependence or whatever condition, and then you're done. So this is something that we'll see very often, or something very much like this in the following theorems. And the example is kind of the same thing. If you have an n-dimensional vector space over a field, then if you take a basis of the vector space, then V, the whole vector space, can be written as the direct sum of the subspaces generated by all the elements of the basis, right? And yeah, so this subspaces are things like these. Just like here, you intended to create, stuff by taking taking integers and multiplying them with the generators. Here you're taking R, the elements from the basis, from the field K, and then you're multiplying them with the generators that you have here. The generators are just the elements of the basis, right? And so these vectors span the whole vector space. And of course, each vector in the vector space has a unique expression like this, as we said before, right? Okay, hopefully everything makes sense as of now. Now this proposition is also important. If you have n abelian groups and you have these H which are subgroups of these abelian groups, then this is very elegant. I mean, this is kind of very straightforward, but also nice. You take the direct sum of all the abelian groups, you mod that out with the direct sum of all the subgroups, and that is isomorphic to taking the whatever that is, external direct sum or Cartesian product of separate quotient groups, right? So G1 mod H1 cross G2 mod H2 up until Gn mod Hn. So that happens to be isomorphic. This looks a lot like the Chinese remainder theorem that we saw during our ring theory lectures. But yeah, and the proof is very much similar. So you define a map from the direct sum of all the abelian groups to the direct sum of all the separate quotient groups, right? So it goes from G1 O plus Gn up until G1 mod H1 O plus Gn mod Hn, right? So these are the quotient groups. And these are of course well-defined quotient groups because subgroups in abelian groups are normal, right? So this works out. Now so this map is defined by taking a tuple of from this direct sum, and then it maps it onto a tuple of cosets, right? Because remember, quotient groups are filled with cosets. So the cosets of course looks like G1 plus H1, G2 plus H2 up until Gn plus Hn. So that's your map, and this is surjective because each of these cosets gets hit by each of the elements from the tuple, and this is a homomorphism. That's very trivial to check. The kernel of this homomorphism is the direct sum of the subgroups. That's also straightforward because the only things which are going to go to the identity by this map are the separate subgroups, H1, H2 and all those stuff. So if you want all the elements that go to the identity, you'll just take the tuple, right, of this. So the tuple of all the elements of the subgroups just form the direct sum of this subgroups, right? And then you apply the first isomorphism theorem, which is that if you have this surjective homomorphism, then you can have the canonical homomorphism, which takes you from this to this direct sum mod the kernel, right? And the kernel is this. So at the end of the day, we're going to get yeah, the first isomorphism theorem just lets you have a unique isomorphism between this mod the kernel to this, and that is basically what we need. I can like write that down and draw, but yeah, there's nothing much to it. Okay, so that was that. Does anyone have any doubts about like how the isomorphism theorem gets the proof done? If you have, then I will just draw the diagram, commutative diagram, but otherwise it's not that hard to see. Everyone good with that? Okay. Let's see. Yep, exactly. JP, you're right. So it's not a fun fact. That's what I was saying, right? You can't pick and choose from Rothman because you never know when he's going back to something, and just pull it out of the magic hat and use it. But yeah. So he defines these subgroups MG, which is just you have an integer M, and this is pretty much like the integers modulo something like 2z, or essentially these are multiples of some of elements of a group. So MG is filled with these MAs, where M is an integer, and this happens to be a subgroup of the abelian group G. So proposition, let's see. So if G is an abelian group and you have a prime number P, then G mod PG, so PG is just this. G mod PG is a vector space over the field of P elements, finite field of P elements. That's the notation that Rothman uses, hopefully. Let me check that. Right, a finite field having Q elements, that's FQ. So that's so he's saying that G mod PG is a vector space, right? Let's see, and this is as JP remarked, is going to be used in the basis theorem soon enough. You take an element from the field, and you take an element from the group. You define scalar multiplication just like you do in vector space in this manner. So the scalar multiplication is just the field element that you have, the scalar times A plus PG. So A plus PG is an element of this, right? So this is a coset of this quotient group, and that is defined as RA plus PG, right? So that's how you define the scalar multiplication for this 2B vector space. It's not yet a vector space, but we're going to prove that. So this formula is well defined if if K is congruent to R mod P, yeah, so this is basically just trying to make sure that you're inside the PG subgroup. So if K is congruent to R mod P, then K can be written as R plus some multiple of P, that is PM. M is an integer. Then Ka plus Pg, that is, Ka is just like Ra plus Pg, essentially something from the field. Ka plus Pg is equal to Ra plus PMA. So PMA in the sense that the elements of Pg are Pa, right? Just like here you have Ma, it will be Pa, and then wait. Okay, I think I missed something here. K is equal to R plus PM. Okay, Ka plus Pg is equal to Ra plus. Okay, so this is just like, okay, you substitute. Okay, I was thinking differently. But replacing K with R plus PM gives you Ra plus PMA plus Pg. And Ra plus PMA is just PMA is already in PG, so Ra plus PG. This just like how you do with cosets in general. Now, so this scalar multiplication is defined. Now you have to check that the scalar multiplication actually is in accordance with the axioms you need for a vector space. And if you remember what you need for a vector space, if you don't, it's not really important to go through, because he doesn't go through it at all, but I think the notes that I had were kind of nice. Yep, so these are the axioms that you need to prove. Wait, this is for a field. Yeah, so this is for vector space. If you have a field, vector space has this scalar multiplication, it has addition, and they are defined like this. And you have to show that, of course, this you have an additive abelian group, and this scalar multiplication is an action of the field on the additive abelian group, right? So this, you have to satisfy these conditions. Rotman doesn't do it. I would say this is a good exercise if you haven't done linear algebra in a while, to show that G mod PG does indeed satisfy all the things you need by this definition of scalar multiplication. Okay, we're going to come back to this later when he goes to Basis Theorem, but let's get into free abelian groups. So free abelian groups, let F be an abelian group generated by these generators X, N. You have N generators. Now if F can be written as the direct sum of cyclic groups generated by each of the generators, where of course each of the cyclic groups is going to be isomorphic to the integers, as we've seen before. But if this is the case, then this abelian group F is called a finitely generated free abelian group, right? So it's generated by a finite number of generators, and it's a free abelian group, and its basis, so you define a basis for this abelian group, and this is analogous to the basis in vector space, but not exactly the same. So the basis is x1, xn, right? And if it helps you, you can think of these x1 till xn as quote-unquote numbers, integers from which you generate the groups of the vector space or whatever. Alright. Okay, proposition 5.9. You have z to the m. So z to the m is just m copies of z, right? And you have to show that this is isomorphic to the direct sum of, it is the direct sum of m copies of z, but if it is isomorphic to any other power of z, then the powers have to be the same. So this is, you see this often in topology, I guess. You have the sphere and the different dimensions of the sphere, and you need the, if you do algebraic topology and you need the fundamental group and stuff, you'll need the direct sum a lot there. And the concept of free abelian groups also appears very much in early homotopy theory. Okay, so the proof is also kind of straightforward. Let's go through it quickly. Okay, so if you have like a group that is like a finite sum of some subgroups, then like a multiple of that, not really multiple, just like if you multiply this group G with some integer, then you have to multiply each of the subgroups in the direct sum with this a multiple, right? Now G mod 2G is isomorphic to the direct sum of all the quotient groups, right? From the proposition that we just saw a few pages back. Alright, so if you calculate the cardinality or the cardinality of this G mod 2G, it'll be 2 to the n, right? Now you do the same for Z to the m. Basically, that if you have Z to the m, then Z to the m mod 2 Z to the m, which is basically h here, then you're going to get the cardinality as 2 to the m, right? Now finally, if you have two things that are isomorphic, 0 to the n and 0 to the m, then the cardinality happens to be the same, right? So if that's the same, then the exponents have to be the same. So straightforward enough. Now there's the other corollary, which I believe is not needed, but if you have a finitely generated free abelian group, then any two bases of F have the same number of elements, the same argument, right? Now this basis that you generate a free abelian group from, the number of elements in that basis is called the rank of the free abelian group, right? And yeah, this theorem right, so yeah, you can see like how this terminology is very much analogous to that of in vector space and linear algebra. So the basis of a free abelian group kind of behaves like that of a vector space, but here's the theorem that makes it concrete. If you have a free abelian group with a basis x, now if G is any abelian group and you have a function going from this basis to that abelian group G, then there is a unique homomorphism G that takes you from F, the free abelian group, to G, and such that everything that you take from the basis is equal with respect to the two functions that you have, the G and the gamma, right? So gxi is equal to gamma of xi, and that's a unique homomorphism. The proof is kind of long. I'm not really. You take an element from the free abelian group. By definition of the free abelian group, it can be expressed uniquely as a summation of these things, linear combination, pretty much, just like in the case of vector spaces. But here you're not taking things from any field. You're taking it from Z, so you have mi as integers. Now you define G, which does the same, but instead of xi, it does mi times gamma of xi, right? So you have this diagram, and what this means is that these two homomorphisms agree on the set of generators that you have, the generators being the elements of the basis, right? And yeah, so these two homomorphisms must be equal, right? Okay. Hungerford observes that this property. Does he? Interesting. That will be interesting, because the category of abelian groups is something we saw very little in Aloofy, but we didn't go much into it. Would be nice. Okay, can you say like which page he says that? Maybe we'll check that later. Okay, yeah. So this was this sets up the foundation for how to treat abelian groups with a basis, right? And how homomorphisms there kind of act like linear transformations in a vector space, right? And the next theorem kind of does the same, but let's see. So if we have an abelian group which contains a subset X, right, with these elements, and A has the property as in the previous theorem, right? So if you have a abelian group G and every function gamma from X to G, blah blah blah, then there is a unique homomorphism G from A to G, which is equal to the function gamma, right? If that's the case, then A, which is just an abelian group, it's not a free abelian group, then A is isomorphic to Zn. That is, if it's isomorphic to Zn, it's a free abelian group of rank n. And this reminds me totally of what we did in homotopy, early homotopy lectures in algebraic topology. Because in trying to find the fundamental group of the circle, you have to deal with the Z a lot, and if you can just show that the fundamental group is kind of a free abelian group generated by these things, then you're kind of done. Okay, so this theorem it's a generalization of the previous one, but let's see if we can go through it. You have the following diagrams, right? So you have the abelian group A, you have the subset X, you have the inclusion of the subset into the abelian group through P. Now X, there is a function from X to Z to the n, that is Q, and you have the same here, right? Okay. So yeah, so this right, the first diagram is just the inclusion of the subset into the abelian group, and yeah, so GP is equal to Q. GP is equal to Q. Right. Okay, yeah, basically you're going to have these two diagrams. Use theorem 5.11, which says that Z to the n is if you have a free abelian group isomorphic to Zn, we have the properties of the homomorphisms being equal, right? Okay, now the goal is if you have if you like merge these two diagrams in some manner, that is, take the composition of G and H, you get something like this. right? So HGP is equal to HQ gives you back P, right? Now HG happens to be this unique homomorphism, okay, but you have the identity as well, right? So identity, the identity on A is equal to HG, the identity map, not the identity as the element. Right. So this is HG, which acts as the identity on A. GH in the reverse order acts as the identity on Z to the N, right? So G happens to be an isomorphism. Okay, yeah. Yeah, I would recommend going through this again to make more sense of this, but it's the proposition which is going to be of more use to us. Okay, finally we have to go to the basis theorem. We're going to introduce some more terminology. Rotman is pretty rough on this. So we include this P-primary stuff, right? So if we have a prime P and an abelian group G, now this abelian group G is P-primary if for each element in the abelian group there is a non-zero number n such that P to the n times A gives you 0, right? So that's a P-primary abelian group. Now if you have any abelian group, then its P-primary component is just all those elements that satisfy the P-primary condition, right? So GP is a subgroup of G. It's not always a subgroup if it's not abelian. If it's abelian, then it's a subgroup. It's a subgroup which contains all the A's from the group G such that P to the n A gives you 0, right? So it satisfies the P-primary condition. Now some more stuff with primary decomposition. So
quick question.
Yep.
So for finite abelian groups, is being P-primary equivalent to being of order P to the K?
For finite abelian groups being P-primary, not, I guess not.
Because, like, just before this, he seems to give a different definition of P-primary. Can you scroll just a tiny bit?
To
the bottom of page 255? There we go.
Okay, so those are P
See,
groups.
it says a P group.
Yeah.
It says, in the context of abelian groups, P groups are called P-primary groups.
Okay,
and there is defined in terms of the order of the group.
Yeah.
But then on the next page, it's defined in terms of, I don't know, being annihilated by multiplying by a multiple of P, or sorry, a power of P.
Yeah.
So I'm guessing that for finite abelian groups, those two ideas are the same.
Right. So P
Whereas
groups,
you could have an infinite abelian group where everything is killed eventually by some power of P.
Yeah.
But then the order is infinite.
Yeah.
Does that make sense? Am I reading that right?
Okay. Yeah, that makes sense. Yeah, I read this remark when I was reading. I just skipped it here. But P group, of course, is the finite group which has order P to the K. Now, I believe if you have a finite abelian group, yeah, this would be pretty much the same. Yep, that's correct. Yeah, sometimes this is confusing. You have P-primary condition, just the P group, and yeah, whatever. Okay, so we have got some. This proof is messy. We'll go through that for that reason. Then we'll introduce pure subgroups, something you probably would not encounter after this lecture ever again. Yeah, maybe in the PSATs. Then a few lemmas, and then the basis theorem at last, and then we have the fundamental theorem. I hope we can do all of this today. Okay, that was P
So
prime.
not to slow us down, but maybe just one more question.
Yep. Okay.
Let's say that we had a finite abelian group and we know its order,
and
we wanted to find its P primary component. So let's say we've got a group of order 72, and we want to find its 2 primary component.
Okay. Yeah.
We just multiply everything by 8, which is the highest power of 2. And then that would be a homomorphism of the group into itself. And then the 2 primary component would be the kernel of that homomorphism.
Wait.
So pick the biggest power of the prime that divides the order of the group, and then just multiply everything by that power. Everything that's sent to 0 is going to be the P primary component, and that'll be a subgroup.
Right, and everything that goes to 0 would constitute the kernel. Right, that homomorphism is interesting. Yeah. Right.
So that way we'd be able to, if it's a group of order 72, then we can find the 2 primary component and the 3 primary component kind of constructively.
Yeah, right. Yeah, you just need to find the kernels of the homomorphisms. Nice.
Okay, I'm back at listening though. Sorry for interrupting.
No, that was very helpful. Yeah, do so whenever you want to. Okay, so yeah, that was that. So primary decomposition, as JP said, is something quite similar. But let's see. So if you have for every finite abelian group G, you have direct sum of its P primary components. So G can be written as GP1. So GP1 is the P1 primary component for the first prime, and you do this for n primes, and then you take the direct sum, then you get the entire G, right? That's for finite abelian group. Then if you have 2 finite abelian groups G and G prime, they are going to be isomorphic only if and only if all of the P primary components of those finite abelian groups are isomorphic to each other, right? And let's go through the proof of this. So what you do, you take an element of G that's non-zero. Cool. Let its order be D. Okay, so its order is D. Now, as you know, D can be decomposed into distinct primes and with exponents. So you write D as P1 to the E1 up until P to the N, sorry, Pn to the En. Now what you do is you have these fractions, pretty much, that is Ri, and that is equal to D over P to the I Ei. So you divide each of the primes with the exponents with the D, and you get Ri, right? So that's just this product without some Pi, right? So what that means is that Pi to the Ei times Ri is equal to D, of course. Now that follows that Ri times X is in GPI, right? So this is also straightforward, because Ri times X, what will be Ri times X? Right. Ri times x is going to be this whole thing times x. Now dx wait is equal to 0. Right, that's because d is the order. Right, and as these things go to 0, okay, yeah, we need to talk about the details. Ri times x is going to be equal to d over pi ei times x, and wait.
And then what characterizes G sub pi is that if you multiply by a power of pi, then you get 0. So basically, if we multiply back in that missing power of p sub I,
okay,
then we get d, which is the order of the group.
Yeah,
like
right.
you say.
Yeah, makes sense. Yeah, I was just not able to multiply those fractions in my head. But yeah. So now what? Your Rix is in the pi primary components of G. GCD, the GCD of all the Ri's here is 1, and that is because the only possible prime divisors of D are the primes that you get from decomposition, right? The n primes that you have here. But each of the pi, the primes, are distinct. They do not divide the Ri's, right? Because because Ri is just like taking a p out of this, and what's left is your Ri. And if you take the p out, then it's not going to divide the whole thing, right? There's nothing else that's a multiple of that, because pi is prime. So pi does not divide Ri. That means the GCD of all these Ri's is 1, right? Now you do the same thing as you do all the time with the GCD, right? So you write the linear combination. So 1 as the GCD can be written as the linear combination of Si Ri, right? For some integers Si. That's the linear combination. Then you multiply this whole thing with x. So x is equal to now the summation of these linear combination times x, right? And this is going to be included in the sum of all the p primary p primary components, and that was that p primary components, yeah. And this is because if you flesh out this linear combination, this summation, you're going to have Si Ri x. Right, so S1 R1x plus S2 R2x dot dot dot. Now each of these is because we just said Rix is already in the p primary components, right? So if you have this integer, it doesn't hurt. It's always going to be 0, and you're going to be in these p primary components, and when you take the summation of all these, you're going to be in the sum of all the p primary components. Right, yeah. Now what you do is you write all the summation of all these p primary components. You write that as hi, but cleverly enough, you pull out one of the primary components, that is gpi. You pull out that, you're left with hi. So this is hi, and what we're trying to show is that okay, so this is where it gets messy really. If your x is in the intersection of a primary p primary component and this hi, remember, so this is very much analogous to what we were doing with the direct sum, right? So he is basically setting up for the direct sum or something like that, because in the direct sum we needed right, whatever that you exclude from the sum, and then you take the intersection with the rest of the sum, you should be left with 0, right? So here you have something similar. When you take GPI, GPI is excluded from this sum, so you take the intersection of this whole thing. Then if there is anything in this intersection, it has to be 0, right? So if x is in this intersection, then x has to be 0, right? Okay. Now since x is in the p primary component, you can write this as like this pi prime to the power of some positive number times x. It vanishes, you have 0. Now it's, as this x is also in hi, you can write x as a unique expression of stuff from the rest of the sum, right? So x is the summation of yj. Now yj are elements of this, right? So as they are elements of this, so you can write pj to the power gj for some right, so he hasn't used the gj anywhere else, right? So gj are some positive exponent. When you multiply these primes with the y, you vanish. So that's that. Now ux is equal to 0, so he defines u to be the okay, to be the product of these pj primes. This is now what you do is these primes with the exponents and these prime with the exponents u are relatively prime, right? They have nothing in common. So as they're relatively prime, so their GCD is 1. As their GCD is 1, you can write 1 as the linear combination of these two things, the linear combination of pi to the l and u. U is just the summation or whatever of the other prime set of primes. So you have two set of primes, and you're trying to which are the two set of primes themselves are relatively prime, and you're trying to form a relationship between them. So this is the GCD of those two things for some integers s and t. The amount of notation he introduces and uses here, and the indices, well, yeah, that's something. So therefore x is equal to where was that? So x is this, x is equal, so you multiply this whole thing with x is equal to spi to the l plus tu, this times x, that is equal to spi to the l x plus tux, and this is equal to 0 because this is equal to 0, as here pix is in the p primary components, and same for ux, they are all in the p primary components, and thus everything vanishes, you get 0, and thus you've proved the first part of the theorem. Give me a second and let me take a breath. Okay, by the way, do you hear any kind of noise from my side? Hopefully not. Okay, cool. Yeah. Okay, so we're not yet even close to the basis theorem, but let's see. The second part of the proof is pretty much the it's pretty much just like trying to have a homomorphism and then trying to have some kind of equality between these primes, right? So your goal is always to use the fact that these things vanish, so that you can do something with them. So let's see. So you have a homomorphism between G and G prime. So they are two pre-abelian groups. Now f of GP, so that's the image of the p primary component of G, is a subset of the p primary component of G prime, right? Right, so now what you do is, you use the special thing about the pre-primary components. Things vanish. You apply the f on those things, and that also vanishes, right? So p to the l times f of a also vanishes, right? Now now you need these isomorphism between the p primary components, right? So if f is an isomorphism between G and G prime, then you will get an inverse, right, which is also going to be an isomorphism. Then from that inverse, you are also going to get this this relation for free. You use that again. Then you also have the restriction, right? So if you restrict f you restrict f from G to just the primary component, and it goes to the primary component G prime P, then that's also going to be an isomorphism. Okay. Now, for the converse, you do the same thing. You have isomorphisms from the pre-primary components. Then from there you can get you get another isomorphism by adding all the p-primary components on both the sides, right? And it's nothing too much. You just have to use the definition of the p-primary components and try to have the homomorphisms. Okay, pure subgroups. Okay, we're one step closer to the basis theorem. If you have prime and G is a p-primary abelian group, then a subgroup is pure if for all the positive integers n, intersection of s with p to the n g gives you p to the n s. So this is interesting because you can see like how many kinds of weird and kind of obscure things he's introducing, right? P to the ng, just like mg, is just like multiples, roughly speaking, of the elements of g, right? With this p to the n. Now, if you look at the definition of p primary components, it contains of p to the n times elements of g that vanish, right? So the goal here is this pure subgroup. Somehow, if we can make these the use of this p to the ng and make it vanish or whatever, then it might be of use. Maybe that's the idea. We'll see that as we go forward. Okay. So that's the case for the pure subgroup. He gives an example. Rotman's examples are just extension of definitions, as I would say. So every direct summand of is a pure subgroup, right? So if we have a abelian group, then its direct summands are pure subgroups, right? So if G can be written as the direct summand of S and T, and S comma 0 is equal to P to the n u v, where u is from S and v is from T. Right. The second example is if you have a cyclic group of order p2, p squared, then S generated from PA, that is, okay, PA is not a pure subgroup, okay, because if you have S written as like PA for some element S in the cyclic group, there is no other element S prime, so that you can write S as P S prime. Okay. And he gives lemmas and examples up until he gets to the basis theorem. Alright. We'll consider some of the lemmas and their proofs, but not all. Okay, so this lemma you have P prime, G is a finite P primary abelian group, then G has a non-zero pure cyclic subgroup, right? So non-zero pure cyclic subgroup just means that you have a cyclic subgroup generated by a non-zero element of the group and it's pure, right? By definition of what we had before. And we are now going to prove this, but as it looks to me, it's not too difficult. You just have to apply the definition of the pure subgroup part and the p primary abelian thing, right? Other than that, I don't see much of an issue with the proof, because the rest of it is just equating these powers of primes with each other. But the proposition of the lemma itself can be important, right? If you have p primary abelian group, then G must have pure cyclic subgroup. Now, definition. Okay, new terminology. If P is a prime and G is a finite p primary abelian group, then the dimension of G, or D of G, is equal to, sorry, D of G is defined as dimension of the other thing that we saw a few pages before, G mod PG. Remember, we made that into a vector space. So if that's a vector space, you can have a dimension of that vector space, right? Because in terms of groups, you don't really have the conception of dimension yet, but as a vector space, you can of course have the dimension of the vector space from the dimension of the basis, right? So so this is D of G, so that's an operation, you might say, definition. So it is additive over direct sum, so D of G O plus H is equal to D of G plus D of H. Yeah. It's additive because we just saw the proposition before. If you have this direct sum mod something, you can that is isomorphic to taking the mod separately and then taking the direct sum, right? Okay. Lemma. If G is not the trivial group, then and is P primary, then the D of G is 1 if and only if G is a cyclic group, right? So if G is cyclic, then so is any quotient of G, right? Every quotient of G is going to be cyclic. In particular, G mod PG is going to be cyclic, right? And if G mod PG is cyclic, then the dimension of G mod PG is 1, because everything that spans that vector space is just 1 prime, right? So that's the dimension of the vector space, S1. And what is that? That's the forward direction. Sorry, that was the backward direction. The forward direction is that if G is P primary and you have D of G as 1, then it must be cyclic. So G mod PG is of course the cyclic subgroup. Wait. Oh, okay. I don't know why I'm messing up with the direction of the proofs, but this statement is the forward direction. We're going to consider the backward direction here. Yeah, apologies for that. G mod PG is cyclic. We know that it is cyclic, then we're going to prove that G is P primary and whatever. So G mod PG is cyclic. So it's generated by the cosets Z plus PG, right? Now G mod PG, of course, as you can see, pretty much that it's isomorphic to integers modulo P, right? Now, integers modulo P is a simple group. Did we introduce simple groups before? I guess not. Or I guess we did during the discussion of group actions, I guess, right?
Remind me, is a simple group one whose only normal subgroups are 0 in the whole group?
Right, so this simple group is, I don't remember. Yeah,
of course,
the normal,
this is Abeilan, so this is any subgroups.
Yeah, the normal subgroups are the only normal subgroups possible are the trivial group and the group itself, right? That's simple, yeah.
Yeah, we did see that. I don't remember doing much with it, but we've seen it.
Yeah, we've seen it. The terminology in Rotman is confusing. He just jumps from one thing to another repeatedly. And just tiring, to say the least. Okay, so integers modulo P is a simple group, right? Because you're taking the mod with P, and the only divisors possible is a 1, which would make you the trivial group, or the whole group P, mod P itself. Now, by correspondence theorem, PG is a maximal proper subgroup of G, right? Yeah, that's directly from the correspondence theorem. I'm not even going to explain how that's the case because it's easy to see, right? Now, we claim that PG is the only maximal proper subgroup. We haven't seen maximal groups before, have we?
I think he just means maximal in the sense that any larger subgroup is going to be G itself.
Okay, so that's
So it's just a subgroup that's not contained in any other proper subgroup.
Yeah, the maximal element of the set of subgroups.
There you go. Or maximal in the set of subgroups.
Yep. With the partial, what is that? Order of containing. If we are to be precise. What is this? So PG, they say, is the only maximal proper subgroup of G. Okay. Now, if L is any maximal proper subgroup, then G mod L is isomorphic to integers modulo P for G mod L is a simple Abeilan group. Okay, well, I guess we'll have to take that for granted as of now, but yeah, it has order.
This is one of those that made sense when I was reading it. I mean, the big picture is that if G mod PG is one-dimensional as a vector space, then it's generated by something with the form Z plus PG.
Yep.
And then this great big paragraph is just arguing that that Z is actually a generator for all of G.
Yeah.
And I'm not following it again at the moment, but I mean, That's what he's trying to prove.
Yeah, that's the goal. To follow, he has this proposition back in chapter 2, where abelian simple groups are precisely the cyclic groups of prime order. I guess we've not seen it, but wait, I guess we have, haven't we? We're dealing with some abelian simple groups and some cyclic groups. Okay, maybe that does make sense to me though. But G mod L is a yeah.
I think that we've shown that for abelian groups, then any divisor, if you pick any divisor of the order of the group, then there's an element of that order.
Yeah.
So that would, this proposition 2107 would follow from that fact.
Yeah, because you have simple and the prime condition. Yeah.
Right, it wouldn't be simple if you had a composite order, or even if your order was a power of a prime.
Yeah.
Because then you could construct a cyclic subgroup that was proper.
Alright, so if A is in G, then P of A plus L, the coset of this G mod L, is equal to 0. It vanishes in G mod L. So that PA is in L. Okay. Hence PG is a subset of L. But PG is maximal. So PG has to be L. Okay. It follows that every proper subgroup of G is contained in PG. Right? That's the maximal condition. In particular, if the cyclic group generated by Z is a proper subgroup of G, then the cyclic group generated by Z has to be a subset of PG. Okay. Contradicting that Z plus PG is a generator of G mod PG. Therefore, G is generated by Z. Right? And G is cyclic. Okay. Okay. Fair enough. What is next? We have a finite P primary abelian group. S is a subgroup of G. The D of G mod S is less than or equal to D mod G, because that's the thing. The notation for subgroups which are not abelian are actually this is less than or equal to. But yeah, here D is just the number. If S is a pure subgroup of G, then the D of G is equal to the D of S and D of G mod S. I believe this is pretty much directly from one of the isomorphism theorems. It looks a lot like that. You have to use something from the vector spaces. Let's see this. And then you have the basis theorem, finally. He gives a couple of proofs of a basis theorem, doesn't he? Yeah, you said that, I guess.
He gives 3 proofs. He gives 2 fairly fully and sketches the third.
So, can we understand the third without the sketches?
I only read the first one because I figured if he put it first, those were the ideas he was trying to emphasize, so I was scared to skip those, but I skipped the others. The feeling for this lemma is he's getting properties of D, and then in the basis theorem he does induction using D, so he does the induction on D using these properties.
Yeah, I see. Yeah, as I said, he's just setting up the stage for himself, and we're to just watch it and follow. But yeah, it's hard to follow. Because yeah, he doesn't give totally. I mean, why he is giving these lemmas. Yeah, but yeah, as you can see, he's trying to construct smooth and nice properties for the D, so that he can in some ways use it as the conception of dimension in the finite abelian group. But yeah, let's see. The proof of this, correspondence theorem says that P of G mod S is equal to P of G PG plus S mod S. The correspondence theorem is it? If you have these cosets. Okay, so these subgroups will be equal to I'm not too sure about that, but I believe if I put my pen and paper down, I'll be able to write that down. Yeah.
That's what I had to do. You have to define this mapping, which is multiplication by P, and look at what the kernel is.
Yeah. The kernel looks not that bad.
But you just have to figure out what the mapping is, and where what is mapping from and to.
Yeah. This is like, this is a grad textbook. You can see, he just makes this equality and doesn't say why it is. Okay, so that's correspondence theorem. So G mod S mod P of G mod S, that's G mod PG, kind of like that, is equal to this thing G mod S mod this whole thing. Okay, because of this equality, you just substitute that is isomorphic to G mod PG plus S, right? By the third isomorphism theorem, which Artin assured us is never necessary, but yeah.
I found my notes. The mapping's just a projection mapping from G onto G mod S. And then P times G mod S is a subgroup of G mod S. So its preimage over in G is going to be a subgroup containing S. And in fact, that subgroup is PG plus S. Or sorry, PG plus S mod S.
Okay.
I think you were right the first time. You need to put pencil to paper and trace back and forth.
Yeah, that's why I believe he gives like these big margins. You have to fill them all with your writing.
Yeah. At least you had us practice the third isomorphism theorem. The next one, part 2, which uses the second isomorphism theorem, I kind of just matched it up side by side with the statement of the second isomorphism theorem without really trying to understand it very well.
Okay.
That's the one that looks like HK mod H intersect K is the same as something mod something else. It's like, or there it is, like H plus K mod H is the same as the big group mod H intersect K or something weird like that. Okay.
Yep.
I'll admit I took this one on faith and moved on to the basis theorem.
Yeah, I mean, well, yeah, I mean, that's why you can see that, he doesn't give explanation for anything, and he's just setting up the stage. He needs these lemmas to work out the theorems. So, he'll just, do whatever he can do to get the proof down.
And my feeling is that this is the number one reason that he introduces pure subgroups, is to have this fact. That in this sense, the pure subgroups divide the groups in this special way.
Yeah.
That the D of G is the sum of, well, if we want to think about it as dimension, the dimension of the big space is equal to the dimension of the little space plus the dimension of the quotient space.
Yeah.
That has a real vector field flavor, right?
Yep.
So if you have a subspace of a vector field, then the dimension of the big vector space is the same as the dimension of the little vector space plus the dimension of the quotient.
Yep.
So that's what he's trying to mimic here.
Yeah. Yeah, he's trying to mimic.
As opposed to just having the inequality that you have in part 1. There's just a general subgroup you just have less that are equal to, and it might be equals.
Yeah.
But if it's a pure subgroup, then it's going to be a strictly less than.
Yeah, the pure subgroup, yeah, would be less than. It cannot be equal, right? Because you have D of S.
So that's what.
Yeah.
That's going to be what allows him to do induction in the next theorem. Okay. Is that if you can find a pure subgroup, then by taking this quotient out, then the quotient is going to have a strictly smaller dimension, or D, and that's going to be the inductive step.
Okay, let's see. Yep, so these two proofs need the second and the third isomorphism theorem. You better get those theorems from Dummett. They're kind of good explained there, and then try the proofs yourself, because going through this is basically useless without pen and paper. Okay, so basis theorem, finally, after all the work. Every finite abelian group G is a direct sum of cyclic groups of prime order, so prime power orders, right? Orders of powers of prime. Okay. So, by the primary decomposition theorem, we assume that G is P primary for some prime P. Now we prove that G is a direct sum of cyclic subgroups by induction on D. Okay, so he starts from 1. Okay, I think I kind of got the big idea. He'll try to find the dimension of the quotient spaces, inductively add them, and play with the primes and their exponents, and then probably get something done. Let's see. Okay, so the base step is easy to see. So the inductive state is we begin by using lemma 5.15. 5.15. I don't remember these numbers. Okay, right. So this was that. If P is prime, then it must have. If G is a P primary abelian group, there exists a pure cyclic subgroup. So you find a non-zero pure cyclic subgroup S that is contained within G. Now, by lemma, the previous lemma, D of the quotient G mod S is equal to D of G minus G of S. Yep, that was the point of the last lemma. And that is equal to D of G minus 1. Right, because your S is a cyclic, pure cyclic subgroup, right? So it's 1. So D of G minus 1 is less than D of G. So yeah, that's great. That's the dimension for G mod S. By induction, G mod S is a direct sum of cyclic subgroups. Alright? We've seen that, yeah. You sum over the cyclic subgroups generated by these xi's, and these xi's are just the cosets that generate the quotient space, right? So that's that. What else? When you take an element from G, you have x bar. Oh yeah, here x bar is just the notation for the cosets, so that's consistent. You have an element from G, x bar has order p to the l, x bar is just x plus s. We claim that there is some z in the group G with z plus s being equal to the coset generated by x, so z generates the same coset as x does. So order of z is equal to the order of the coset generated by x bar. Right. Now x has order p to the n, where n is greater than or equal to l. Okay. But p to the l times x plus s, the coset, is equal to p to the l times the coset generated by x, that is equal to 0 in G mod s, because it is pure, and you have the p primary condition. So there is some s such that p to the l x is equal to s, right? Okay. Right, because p to the l x bar is 0, p to the l x, that must be equal to some s. Now, by purity, there is some s prime such that p to the l x is equal to p to the l s prime. Good lord. And if we have z is equal to x minus s prime, then p to the l of z is equal to 0, and z plus s is equal to z plus x plus s. Yeah, we know that already. Z has order p to the m must be greater than or equal to 0, sorry, l, because z gets mapped to x bar. Wait. Since p to the l of z is equal to 0, the order of z is equal to p to the l. Okay, all of this makes some sense to me, except I'll have to put the pen and paper down to make sure I totally understand it. Okay, now for each I, choose a zi with zi plus s being equal to I mean, you can do the same thing from the beginning, like he does, like for 1z 1x, and then he does for zi. Good lord. So it follows the same condition. Order of zi is equal to the order of the coset generated by xi. Now we define t to be generated by these z's. So t is equal to cyclic group generated by these generators. Now s plus t is g, because g generates s. Sorry, g is generated by s and zi's, right? Zi's generate t, and s, of course, s, of course, where is that? When you add that with the elements of, yeah, I mean, right, see, your t is generated by these zi's, So when you have s plus t, you will have something from s, that is these xi's or whatever, and then you will add that with z, right? So zi plus s is going to give you xi plus s, and this is just an g. So g is generated by s and the t. To see that it's a direct sum, we'll have to prove the other condition, that they intersect at 0. Give me a minute. Okay, I'll be right back. Okay, I'm back. Yeah, so the thing is, my days are messed up. I don't sleep, I don't eat, so I needed to get my dinner. Yeah, so we're back at the basis theorem. Yeah, so T, we have to show that they are intersecting at 0. So if you have something in this intersection, then of course you apply the same thing, right? Y can be written as the linear combination of mi and zi, where you know, your mi's are the integers. Now if y is an s, then it vanishes, right? Because you have the p primer condition there. Yeah, in G mod S. So then, since this is a direct sum, each mi xi bar, right, the cosets, is equal to 0. So for each I, this weird looking sum, what this is trying to say is that when you add this, all the mi times the cosets with the mj times the cosets, summation of those, linear combination of those, you're going to get 0. And this thing belongs to the this is exactly what we were saying before, si intersection, the summation that excludes the si. So here the cyclic group generated by xi and the cosets of it is excluded from the sum, and this thing is that. So this is equal to 0. Therefore mi zi is equal to 0 for all I, hence y is equal to 0, right? So this is a direct sum indeed. Finally, g is equal to s o plus t implies d of g is equal to d of s plus d of t, right? And that is equal to 1 plus dt, just that, so that d of t is less than d of g, and by induction t is going to be a direct sum of the cyclic subgroups zi's that separately generated. Alright, so that was the basis theorem. And now I feel like, it's kind of trivial. It's like, he just puts in all the arguments from his previous lemmas and just ties them in a nice way, and it works, because there is nothing new in this proof. It's just using whatever he has stated before, right?
Right. I mean, that's just an elegant way of presenting stuff.
Yep.
I mean, it's even worse when he gets to the fundamental theorem. By the time he gets to the fundamental theorem, he basically says this is a direct consequence of all the work we've done before. I'm trying to find where it is. Yeah. Theorem 5.25, Fundamental Theorem of Finite Abelian Groups, and it's got like a 2.5-line proof.
Oh.
The result follows from Corollary 5.24.
Well, that has to be the shortest.
So, the place where I think we are now is, first of all, we did the primary decomposition, which says that we can break it apart into subgroups of prime power orders.
Yep.
And then the basis theorem is saying that those prime power subgroups can further be broken down into direct sums of cyclic subgroups.
Yep.
What we now have is that for every finite abelian group, we can write it as the direct sum of z3 plus z3 plus z9 plus z27 plus z5 plus z5 plus z25, but basically powers of primes. But the only thing that he hasn't done is prove the uniqueness part now. He proved the uniqueness of primary decomposition, but not for this last bit of the way that we're decomposing the prime power subgroups. So that's the part that's happening next, and it feels like that part is going to be constructive. This induction proof may have been constructive, but I didn't understand it well enough to say that it is. What I think is coming up is, let's say that the mystery group that we're trying to figure out is Z mod 3Z, I'll just call that Z3. So it's Z mod 3 cross Z mod 3 cross Z mod 9. And we're trying to figure that out. So first of all, we're going to look at the whole group mod 3 times the group. Well, if I take 3 times that group, then those 2 3z's disappear.
Yep.
So when I take the quotient, I'm going to get something one-dimensional. So that allows me, that way I've just figured out that I have 2 factors of z mod 3 in there. So if I were building up, I would then take 3 times the group mod 9 times the group. And then that would tell me the number of factors I have of that are multiples of z9, or that are copies of z9. And then I'll take like 27g mod 9z, or the other way around, 9z mod 27 times the group. So I think that that's what he's building up to get these numbers d that he's working on.
Yeah.
So that feels more constructive. Kind of like that game I was telling you about earlier. Like, if you want to figure it out, I get to ask you a finite number of questions. Like, well, what's the dimension of the vector space 9 times g mod 27 times g? It's like, okay, that's 2. Okay, that just told me that I've got 2 copies of z 27.
Yeah.
So anyway, I think that that's where we're going. But I don't know, are you getting worn out? Do we need to?
No, I think we have 5 more pages, so we can go through that. Yeah.
Okay, you're going to skip ahead to the fundamental theorem.
I guess these lemmas, I'm not sure. I mean, he proves like 2 other things. Sorry, 2 other proofs of basis, right?
Right.
Good lord. Yeah. So yeah, we're doing some good stuff. Like, this is another level of prime factorization that we learned in middle school. Yeah, let me just finish this thing. Okay, so I believe the lemmas that come after this are not as necessary for the fundamental theorem, or are they?
I think we can safely skip ahead to the middle of page 262.
262. Okay, fundamental theorem. I see.
That's just skipping those 2 alternate proofs.
Yeah. And the shortest proof that he was talking about, it was short, but I'm not sure like how interesting or like. This is the fundamental fundamental theorem, and I believe so he proves the fundamental theorem, and then the basis theorem is like a special case of that.
No, I think, well, yes, it's not a special case, but it's a big ingredient.
Yeah. At least he doesn't spend 20 pages building up lemmas for at least, he has like ABC lemmas, so that's okay. 3 lemmas. We can go.
I guess the weird thing is it doesn't really seem like it's saying, oh yeah, there it is, on page 264. It's like we already know that it can be broken down, but this is showing the uniqueness part. That they're isomorphic if and only if they have the same elementary divisors.
Yeah.
And it's constructive in the sense that for any particular group, you can figure out, it's possible to calculate what those elementary divisors are.
And he gives an example which contains numbers, so that's something.
Oh my god. So now we only have 2 pages to go.
Yeah, 2 pages and a lot of notation. This is scary. Okay, Fundamental Theorem. Here we go. We have defined that the dimension of a group is equal to the dimension of the vector space that you generate G mod PG, and D of P to the NG is equal to the dimension of P to the NG over P to the N plus 1G, right? So, yeah. Okay. So lemma 5.22, which says that G be a finite P primary abelian group where P is prime and G is the summation of these cyclic groups. If B to the Bn are like positive, okay, so Bn is the number of summons Cj having order P to the n. Okay, so the cyclic groups that have order P to the n are Bn. Then there is some T with this. I don't understand this. G is a sum of these cyclic groups. Okay. Now the number of cyclic groups that have order P to the n are Bn. Okay. Now, if that's the case, then you have some non-zero T such that the dimension of P to the NG is equal to the it's equal to Bn plus 1 plus Bn plus 2 up until Bt. So you can just have the number of summons that have order P to the n, and from there you'll be able to calculate the dimension of P to the NG. That sounds cool. So let Bn, capital Bn, be the direct sum. That's the thing, he introduces all kinds of notation, and this is like good in the like mathematical sense, it's like very structured, whatever. But like when reading it, no, it's terrible. Yeah, Bn is the direct sum of all the C's you have there, with order P to the n, if there are any. Thus, G is going to be the direct sum of all the B's you have there up until T, right? So P and G is equal to P to the n of all these B's, right? And then you take the direct sum. And that's because P to the n Bj is going to be 0 for all n, because they're all cyclic. Right. And they have order P to the n. Yep. Similarly, P to the n plus 1g is just going to be the same thing, but for n plus 1, P to the n plus 1. Now proposition 5.7, which was, I don't remember exactly, but I believe it was about this quotient space being isomorphic to the direct sum, taken the mod taken separately. So Png mod P to the n plus 1g is isomorphic to the series of this the summation of all these quotient spaces, right, of P to the n b mod p to the n plus 1 b, right? For all the b's you have up from n plus 1 till t, right? So that's that. Now exercise 5.7 on 267 gives us this. God, I mean, you know, like referring back to previous exercises is one thing, but referring to like upcoming exercises is like, it doesn't make sense. Like, what do you mean? Like, to understand this theorem, we have to like go ahead and do that problem. Okay. So this exercise, which we'll have to look what that is, but that just gives us the fact that d of Pn Bm mod Pn plus 1b is equal to dimension of the p to the n Bm, right, which is a vector space. Okay. I'm not exactly sure how that'll work, because I'm not sure how that problem is stated or how that'll be proven. But yeah. D is additive over direct sums. So d of p to the ng is just the summation of the lowercase b's, right? Because the dimension of p to the nb is just the lowercase b's. By definition, the number of summands you have. The number bn can now be described in terms of g. Does that really make sense? I mean, I get the idea what he's trying to do, but so theorem 5.23, we have a definition here. Let's see. So the definition says that if you have a finite pre-primary abelian group, you can define up of ng as the dimension of p to the ng minus dimension of p to the n plus 1. Why do you need a whole new definition for that? Good lord. And a whole new different inconsistent notation like up. You have to remember this whole thing again. Up of ng is the dimension of p to the ng minus the dimension of the p to the n plus 1g. Dimension of p to the ng is equal to the b's from n plus 1 till bt. Of p to the n plus 1g is b to the n bn plus 2 till bt, right? And when you subtract, you're going to get b to the n plus 1. So bn plus 1. Yeah.
So why does he have to introduce u sub p n comma g when that's the same as b sub n plus 1? We already have a name for it.
Indeed. I mean, I don't know why he's doing this.
Why don't we just call it bn plus 1?
Yeah. So theorem 5.23. If P is a prime, then any two decompositions of a finite P primary abelian group G into direct sums of cyclic groups have the same number of cyclic summands of each side, right? So your B's would be the same. More precisely, for each positive n, the number of cyclic summands having order P to the n plus 1 is bn plus 1. That is upng. Yeah. upng. Okay, so the proof, basis theorem. You can write G as a summation of direct sums of cyclic groups, right? That works. The lemma before us, before this, shows that for each n greater than or equal to 0, the number of cyclic subgroups having order p to the n plus 1 is bn plus 1, up and g. A number that is defined without any mention of the given decomposition of g into a direct sum of cyclics. Right, so he is trying to you know, go away from the cyclics. I believe cyclics are not something he wants to deal with, and that's why he introduced this.
I think he's emphasizing that these numbers can be generated just by looking at the group.
Yep.
It's like, you give me the group, I'm going to take 3 times the group mod 9 times the group, and then I'm going to do 9 times the group mod 27 times the group, and then subtract those numbers, and then that's going to tell me the number of factors of a certain type.
Yep, I don't have to
worry
about,
without having to do any kind of decomposition first. Yeah, that makes sense.
So that's that. So without any mention of the given decomposition of G into a direct sum of cyclics. Okay. Now, if G is another decomposition with these D's, where each D is cyclic, then the number of D having order Pn plus 1 is also going to be the same, right, as desired. Didn't he just state that? Did he prove anything? he just stated it. Okay, the corollary of this is that if you have two finite p primary abelian groups, then they're going to be isomorphic. If and only if these up numbers for these two primary abelian groups are going to be the same, right? And that is a big deal, right? If you can make these b's the same, then your groups are isomorphic. What a nice thing. Proof. If your phi from G to G prime is an isomorphism, then the image of p to the n g is equal to p to the n g prime, right? Yeah. And so phi induces isomorphisms of the vector spaces fp, okay, the finite field of p elements, the vector spaces based on that field, and these are the vector spaces png mod pn plus 1g, which is isomorphic to png prime mod pn plus 1g prime, right? Because your images are the same. So this isomorphism is in terms of the isomorphism of vector spaces, right? Which means that okay, your png plus pn plus 1g, right? So that's the whole thing is a coset, right, yeah. Your pn plus 1g is the normal subgroup you're taking mod of, right? Okay, yeah, that gets mapped to pn times phi of g, the image of g, plus the other normal subgroup pn plus 1g prime. So this is the coset. So you go from one coset to another and that's an isomorphism. The dimensions are going to be the same because they're isomorphic as vector spaces, right? So that means your UPs are going to be the same. Yeah. Cool. Now converse, because this is an if and only if statement, right? Conversely, if you assume that your UPs are the same for all n, then if G has some decomposition of C's and G prime has some decomposition of C primes, cyclic groups, then by lemma 5.22 we show that there are the same number of summons of each type. So it is simple it is a simple matter to construct an isomorphism, right? Yeah, 5.22, which is this does that for us. Okay, so I guess we know where we're going. The last thing we need to know is the elementary divisors. If G is a P primary abelian group, then its elementary divisors are the numbers in the sequence having UP 0G P's. Wait. UP 0G P's UP 1G P square. Okay. Up until UPT minus 1G PT, where PT is the largest order. Okay, so P. Okay, so here these primes are the orders of the cyclic groups or whatever, and the UPs are the then that number we need the count for the cyclic groups. So those are the elementary divisors. Right, the numbers in the sequence. If G is a finite abelian group, here is just a P primary abelian group, so it can be infinite. Wait, yeah, maybe. Or if G is just a finite abelian group, not P primary, I guess, then its elementary divisors are the elementary divisors of the primary components. Okay, yeah, essentially for elementary divisors you need the primary components. And theorem 5.25, the fundamental theorem, is that two finite abelian groups are isomorphic if and only if they have the same elementary divisors, right? So that means any two decompositions of these two finite abelian groups into cyclic groups have the same number of summands of each other, right? And this follows directly from the definition of elementary divisors, theorem 5. And theorem 5.24, which the corollary is, that was the big deal here, right? Yeah, we're done. Okay, let's look at this example. Or maybe after this it still goes on. Exponent, invariant factors, whatnot. Okay, I don't think we'll go through this. Fundamental theorem was enough. But yeah, let's go to this example in terms of numbers. So how many abelian groups are there of order 72? Well, now 72 is 2 cubed times 3 squared. So that any abelian group of order 72 is the direct sum of groups of order 8 and order 9. Yep. There are 3 groups of order 8. Yeah. Described by the elementary divisors. Described by the elementary divisors 2, 2, 2, 2, 4, and 8. There are 2 groups of order 9 described by elementary divisors 3, 3, and 9. Therefore, to isomorphism, there are 6 abelian groups of order 72. Okay. I guess I get the idea, but not sure if I get. I mean, yeah. Okay. After this, he goes on to do some second type of decomposition. Of course, he has a lot of time. 1,000 pages book, so he can do anything.
So I guess just reading the statement of proposition 527 gives the idea of what this other way of breaking it down is. So you can also write it as the direct sum of cyclic groups where the orders divide in this way.
Yeah.
So I think what's happening here is, let's say that you had something that was broken down as Z2 cross Z2 cross Z3 cross Z9. I think he's just observing, since 2 and 3 are relatively prime, we just put those together because Z2 cross Z3 is the same as Z6. So Z6 might be one of the... 6 might be our C1 in this list. So it's like grouping together the ones that are relatively prime into a single summand. But I don't know exactly how it works, but I think that's the gist of what's happening here.
Does Hungerford do something similar?
I think that Hungerford does this decomposition first, and then does the other one.
He does the other one?
I think he does this one first, the one with the C1 divides C2.
Okay.
And then he separately, or after that, talks about the other one. I'm not positive. I think that's what Fraley does. Not Fraley, whatever other one I was looking at yesterday.
Yeah. I probably have to look into Hungerford too. Yeah, this is heavy stuff. But okay, we at least made it. Yeah, so I would say going to Rotman again and doing some of the problems that he cites in exercises, it's a good idea, and stuff like that. And we have the P set. I don't have the P set ready. I'll try to do this by tonight, and yeah, next week we're going to have 2 more sessions on 2 more lectures on this group theory, and we'll do the Scalar theorems and the Jordan-Holder theorem.
Yeah, Hungerford on page 78 has his version. An interesting part is that he also deals with having a free part. So he allows copies of Z in his list. Then for the finitely generated part, if you see theorem 2 points, there you go. So the F in that sum is a freely generated, or is a free abelian group. So that's just a bunch of copies of Z. But then notice how he's got that division thing where M1 divides M2 and so forth. But if you flip to page 81, you can see how he has an example about halfway down, where he's taking it kind of from one way of writing it into another way of writing it.
Looks like it.
So,
yeah,
where it says by limit 2.3, G is isomorphic to, and then he has it written in a funny order, but it's Z3 plus Z9 plus Z27 plus a couple of copies of Z5. Then there's a Z25. Oops. So if we wrote those in order from smallest to largest, that would be the decomposition that we just did in Rotman.
Yeah.
So if you look in the 2 primary subgroup for this G, that would be Z2 plus Z4. And the 3 primary subgroup is a Z3 plus Z9 plus Z27.
Yeah.
So you could go through with the primes that way. But then you see he's rearranging things and saying that if you reorganize this, then the same G can be written as Z15 plus Z90 plus Z2700. And you got 15 dividing 90 dividing 2700.
Yeah. Okay, so
and that's using like Z2 plus, or Z3 plus Z5 is the same as Z15. So we're going to go ahead and group those together.
Indeed.
And then that Z90 is another group of several things.
Yeah. So Rotman.
So I think that every author is just going to pick one of these versions to prove And then just by rearranging factors, you get the other versions.
Yeah, I hope that's that easy as you're saying in Rotman, because he likes to make things difficult.
Yeah, my gut feeling is that rather than reading the rest of the section of Rotman in detail, I'm going to read the examples over in Hungerford, and then do whatever example or whatever exercises you pick out for us.
You have, I don't know, invariant factors.
He does talk about that. Hungerford does talk about invariant factors also, as well as elementary divisors.
You see.
So on page 80, you might be making the connection between the invariant factors and the elementary divisors.
Yep, looks like it. There's a lot to go through.
Just to put a bug in your ear, it sounds like we might get some good homework problems out of Hungerford rather than Rotman.
Okay. Yeah. Yep. So yeah.
Oh, thanks. That was a long session, but it was a very, very dense section. There's a lot to make sense of.
Yeah, and
I think I'm going to try to get an earlier start on next week's readings.
Yeah. I guess Scalar theorems would not be that. I can't say Rotman. Well, I don't know what Rotman is going to do. Yeah. So.
But you can read about those in pretty much any book. So
yeah.
If I get too lost in Rotman, I'm just going to go read somewhere else.
Yep. Same. Okay. So see ya next Tuesday. Yeah, we'll meet for Scalar theorems.
Yeah, thanks a lot. Get some sleep this weekend.
Okay, yeah. See ya.